In this video, we'll talk about methods for choosing which variables should be included in regression models. Let's orient where we are in terms of the overall flow of our course. We've discussed how to evaluate models with quantitative metrics and plots, and by using cross-validation to understand out-of-sample predictive performance. Now that we have this set of tools for assessing the quality of models, we'll put them to use by talking about methods for building models. To motivate why there's particular interest in methods that help build models, let's take a glimpse at the New York housing data that we've looked at previously. We see that there are 15 predictors to consider when building models for house price. That's a lot to consider. In this video, we'll begin our tour of methods that can help with this. Generally, the area of statistical methods that deals with the task of what predictors to use in model building is called model selection. There are a few general spheres of model selection methods that we'll consider in this course. The first general area is subset selection, which is the subject of this video. Subset selection methods look at different subsets of predictors to build the best model. What does best mean? Best refers to whatever quality metric we've chosen. For example, a test error estimate from cross-validation or the validation set approach. For subset selection methods, we'll look at best subset selection and forward and backward stepwise selection methods. The second general area is called shrinkage or regularization, which we'll talk about next. The idea behind these methods is to penalize the inclusion of predictors that are only weakly informative of the response. Methods in this area include a method called lasso, ridge regression, and the elastic net. The last area is dimension reduction. The idea here is to reduce the number of predictors by creating new predictors that are functions of the existing ones. We'll look at principal components regression a bit later in the course when we talk about unsupervised learning and principal components analysis. But let's start our tour of subset selection methods by talking about best subset selection. When we have p predictors, there are 2 to the p possible models that can be formed from the inclusion and exclusion of these predictors. Why? Because for every predictor, there are 2 choices: include it or exclude it. 2 choices for each of p predictors results in 2 to the p possible models. In a best subset selection procedure, all of these models are fit, and we choose the one with the optimal value of our chosen evaluation metric. Remember that this metric should be a metric that fairly assesses test performance of the model, in contrast to training set performance. For example, with 4 variables, there are 16 models to fit. 4 one-variable models, 6 two-variable models, 4 three-variable models, and 1 four-variable model, and 1 zero-variable model. The zero-variable model being one with just an intercept. Oftentimes, software that implements best subset selection will provide users with the best model of each size. Best subset selection is conceptually simple. It just tries all possible models formed from including and excluding variables. However, it does not automatically try transformations of the predictors or interactions between variables, which can certainly be important. If we want to explore them, we have to manually include the transformed variables or interaction terms before running the algorithm. Another downside is that best subset selection is computationally expensive. With just 10 predictors, over 1,000 models have to be fit. As we get more predictors, it quickly becomes infeasible to even run best subset selection. This computational time limitation is the main motivator for exploring forward and backward stepwise selection. So in forward stepwise selection, the idea is to add variables to a model one at a time, choosing the best variable to add each time. Again, best refers to the model quality metric chosen. One important historical note about the selection metric is that many past and current implementations of stepwise selection choose the best variable as the one that has the lowest p-value from a hypothesis test of the regression coefficient. This approach is problematic for a number of reasons, which we'll discuss towards the end of the video. But in our discussions, we are going to use cross-validated estimates of test error, which work better than selection based on p-values. So let's step through the forward selection process. We start with an empty model that only has an intercept, and in this first stage, we consider all of the single variable models. So in this example, there are 4 predictors, so we consider models with just predictor A, just B, just C, and just a D. Turns out, adding C results in a model with the lowest cross-validated mean squared error, so we add it to the model. In the next stage, we start from a model with predictor C. We consider then adding A, B, or D. The model that adds A ends up resulting in the lowest cross-validated mean squared error. So in the third stage, we start from the C plus A model and consider adding B or D. It turns out adding B results in the lowest cross-validated mean squared error. And in the last stage, we start with a C plus A plus B model and only have D left to consider. So we end up with the best 1, 2, 3, and 4 variable models. And to choose one final model from these 4, we can choose the one with the optimal error metric. This time, best is in quotes because the models selected in forward stepwise selection might not actually be the best 2 and 3 variable models. Why? Because stepwise selection methods are so-called greedy algorithms, they don't fit all possible models. In the first stage, all possible 1 variable models are fit, and there's only one possible 4 variable model which is fit. But not all of the 2 and 3 variable models are explored because we restrict ourselves to models that contain C in stage 2 and models that contain both C and A in stage 3. This behavior is called greedy behavior because the algorithm uses a heuristic to save time instead of finding the overall optimal solution. This is a great improvement on computational time over best subset selection, but it is possible to miss the overall best model because we won't explore all of them. Also, like best subset selection, forward selection doesn't automatically try transformations of predictors and interactions. We have to manually include them in our data to explore them. Backward stepwise selection is similar to forward, but instead removes variables one at a time, each time removing the worst or least useful variable. Just like best, worst refers to the evaluation metric used. Implementations that use p-values choose the variable with the highest p-value to remove, but we will continue using cross-validated estimates of test error. We start with a full model that has all predictors, and in the first stage, we consider removing each one of the 4 predictors. Removing either B, C, or D results in a high cross-validated mean squared error, suggesting that they are useful predictors because error goes up a lot when they are removed from the model. On the other hand, removing A results in the lowest cross-validated mean squared error, suggesting that it is the weakest predictor of the 4. Removing it does the least harm. So we remove A, and in stage 2, we start with a model with B, C, and D. We consider removing one of those 3 predictors. This time, removing B and retaining C and D results in a model with the lowest cross-validated mean squared error. Removing B does the least harm. So in stage 3, we remove B and start with a C plus D model. We consider removing one of them. This time, removing D does the least harm. And in the last stage, we remove D, and we're left with a single one variable model with just C. As with forward stepwise selection, we end up with 4 models that we can choose from with our error metric. Note that backwards and forward selection can give different results because of the greedy behavior. Not all possible models are fit, and it's possible for forward and backward selection to look at different subsets of models and thus give different results. An important point is that as machine learning practitioners, we'll often be in cases where there are several reasonable methods to try. Here, for example, both forward and backward selection are reasonable methods if computational time prohibits best subset selection. And when we have many methods that are reasonable for a task, trying several of them, comparing their results, and reporting all results is key to doing good science. So it's worth making note of some cautions surrounding these automated selection methods. For one, many statisticians feel that automated variable selection methods encourage practitioners to not think carefully about the data because you can just dump your data into an algorithm and get out a model. Deep and careful contextual thinking is so essential in all research settings, and careless use of automated procedures can result in real harm. Another concern relates to the historically widespread use of p values for selection. Using p values results in unstable and often undesirable results when several predictors are correlated with each other, which is a phenomenon known as collinearity. There are also clear problems that have been demonstrated with statistical inference on the final selected model from these automated procedures. Because we come to select a final model by trying a large number of models, multiple hypothesis testing is a big issue. With multiple testing, the idea is that testing many hypotheses runs the risk of a result being statistically significant just by chance. To cite a few problems with inference, the coefficient estimates tend to be overestimated, the confidence intervals on the coefficients are misleadingly narrow, and p-values are misleadingly small, and they don't mean what they should due to the multiple hypothesis testing. If we think about what is happening in these variable selection procedures, we can see why these issues arise. At each stage of selection, we are fishing for the best possible predictor. So, in summary, we've looked at subset selection methods that use model quality metrics to search through different models to guide model building in an automated way. Best subset selection is intuitive but computationally expensive with large numbers of predictors. Stepwise selection methods are faster, but aren't guaranteed to find the best subset of predictors. They're greedy algorithms. None of these methods automatically consider variable transformations or interactions. We have to manually include transformations or interaction terms to explore them. And finally, these methods have problems with statistical inference on the final selected model. Generally, the shrinkage or regularization methods that we'll cover next are preferred choices in the statistical and machine learning communities, but it is important that you've heard about these subset selection methods because they were very popular and still appear in the literature today.